Hi, hi, I'm Mano. Today I wanted to show you how to not only how to choose but how to decide and compare different kind of power MOSFETs. What we want to test today is the gate charge and the turn on, turn off. So there are, if you see some datasheet, you can find different type of circuits, but anyway, the principle is this: you have a constant voltage, and you have a current source with a diode, and here you have your MOSFET with a pulse on the gate with a fixed RG resistor, and this will be your VI. So basically what you're going to see with this kind of circuit, there are different types of circuits. You can even put a diode here with another voltage here. Anyway, there are so many circuits, but today we'll analyze just the simplest one. So basically what is going to happen in this kind of circuit is that you apply a voltage on the gate like this, and the voltage VDS will be like this, because when the MOSFET is off, between the drain and the source you basically have the voltage V1, let's see, 20 volts, and the current has exactly the opposite behavior. So you will see something like this. As you can see, the switching the dissipated power will be in the interval of the switching, turn on and turn off. So you will have something like this. Now, what we want to analyze today is how this curve is gonna charge. It won't be something like this, but something like this instead, with two different taus. Because if you watched my videos, I explained how the capacitors, how the parasitic capacitance of this MOSFET varies with respect of the applied voltage. In particular, there is a nonlinear capacitor called CDS, which is the capacitance between the drain and the source. This capacitor can assume two kind of values with respect of the voltage VDS applied. And so this is the reason why you will see two different increases, because the tau 1 will be different from this tau 2 here, because the value of the CDS has varied between CO1 and CO2 basically. So let's simulate this circuit on LTSpice, and let's compare with any kind of MOSFET that we can see, and you can use also IGBT to analyze the effect of the tailing effect, for instance. So let's do this. To simulate the turn on turn off of the MOSFET, you can use a pulse generator with a duty cycle D of 0.5 and a switching frequency of 100 kHz, which is the typical switching frequency of the MOSFET. You can go even higher if you want, but anyway. So let's put a pulse between 0 and 5 volts. Should be enough to turn on your transistor. The delay 0, and the rise time is 1 nanoseconds both for the rise and the fall. T on D over Fs. You already know the story, and the period is 1 over Fs. So you have your pulse. Now you choose a MOSFET, any kind of MOSFET that you want. Let's pick the first on the list, and let's pick a gate resistor RG with 5 ohms to start. So now let's use a constant current here. You can also put an inductor if you want, but it is more effective, and a diode, a freewheeling diode. let's put a voltage here of 20 volts. And what we want to see on the, let's put 2 amps for instance, what we want to see on the plot. So let's analyze here the gate VG. This is the pulse, it's called with P. It should be slower because there is the gate resistor. And let's compute then the power and both current and of course we can do it with a behavioral voltage or with directly with the plot. So let's run the simulation for 10 milliseconds. And so this will be the voltage that I am giving at the gate. And since there is the gate resistor, it will be a little slower. This is useful because basically you don't have you don't want always a so fast rise time, because you can induce high dV over the T, which can cause ME emission, which is something that you don't want. So as you can see, in the rise time of the gate, there are 2 different transients, and that's because basically there is 2 kind of taus, as explained here in also in another videos. And now let's analyze the drain voltage. So as you can see, the drain is switching between 0 and 20 volts, and the current which is flowing is exactly the opposite. So as you can see, most of the dissipation will be in this interval. Now let's add another plot. So here we have the gate voltage, the drain, current and voltage. And now let's compute the power. You can click Alt in the Mosfet and it will give a very complex expression. I think that what you can do, you can directly do something which is very easy, which is way easier in my opinion. Yes, that will be the real dissipated power, but you can do something easier. You can write right there to the drain voltage, and now you can multiplicate it for the current, so for the voltage, and 002, and now you have basically exactly the same result. So what is going on here? You have 2 kinds of power. Let's forget for a second the spikes. I think that I have to slow down the time simulation for 100 microseconds and just slow down this voltage of 10 volts so that I can appreciate more the power dissipation. Still high, so let's use a lower current. Yeah, it's still high. So now let's see what is going on here. So as you can see, in these 2 intervals, you have the dissipated power in this interval here, which is called the conduction losses. As you can see, the value is very low. If I draw the cursor position, you see that the power dissipated is something of nanowatt. So basically nothing. In this interval here there is always nanowatt. It is never so slow. It is never so low. But instead, in the switching phase, I have something like 7 watts, which can be real. Now the fun begins when you choose another Mosfet. You replicate the circuit and you choose another Mosfet with the same parameters. Let's choose another Mosfet of the list, but remember that you have to change this net here. So let's use instead of this, let's use another Mosfet which has a higher on resistance. Not so high, but maybe higher. Yes, 46 milliohms. So, what is going to happen? Oh, yeah, of course I have to. Everything has changed. So, yeah, just you. Let's cancel off this. So now I want to compare first the true rise time of the VDS and even the of the VG. So let's put okay. So these are the true gate voltages. As you can see, the with the same Aron resistor, the MOSFET on the right is a bit faster than the MOSFET on the left. I suppose the reason is why the gate charge is different. So let's see if it is true. Yes, that's the reason why. So on the right you have a MOSFET with a higher Aron, but as you can see the gate charge is lower. So as you can see, the rise time with the same gate resistor, it is still higher. So the difference is this MOSFET has lower gate charge. So it turns on faster. Yeah, as you can see, it turns off. But it has a higher Aron resistance. So it means that we expect to have higher conduction losses. Because remember that the conduction losses are P equal to RDS times I square. So the higher the RDS on and the higher the conduction losses. Let's see if this is true. It should be true. Let's calculate this and let's calculate this. So what is going on here? The switching losses on the right, on the left are higher. On the left MOSFET are higher. This can be true because it is a bit slower. But the MOSFET on the right, as you can expect, let me compare the conduction losses because it should be higher. Yes, it is. Oh, yes. As you can see, the dissipated power of the conduction of the MOSFET on the right, it is true that it has higher it has a lower gate charge, but as you can see, the dissipation power is 60 milliwatts. So now, if you calculate the integral of this, you should see that the average power is 69 milliwatts, and instead the gated power of this is 58 milliwatts. So now let's zoom again and let's calculate the integral of these two. You have 37 milliwatts in this period, and in the red you have 32 milliwatts. So, as you can see, the MOSFET, the red MOSFET, which is ID, which is M1, it has average less dissipated power. So, as you can see, there is you have to understand that there should be a trade-off between gate charge and, of course, power dissipation. So on the other side, you have faster gate charge, faster turn on because the gate charge is lower, but you have higher dissipation. It depends on your application, of course. Now let's destroy this MOSFET. Let's use not a MOSFET, but let's use, for instance, an IGBT. IGBT are power devices. IGBTs are power devices. Oh my! I don't remember how it is called. By the way, this is another simulation which I want to show you, which you have a silicon MOSFET and you have two kind of GaN devices. So let's run this simulation, and as you can see, I made something which is very similar to before. Basically, here you have other gates, different gate charges. So as you can see, the GaN device is way faster than the others. So this is another example simulation of GaN devices. This is APC. APC stands for Efficient Power Converters, and these GaN are used for power electronics application because, as you can see, they have a faster rise time even with a 10 ohm gate resistor. So that's really beautiful. And don't take for granted that MOSFET will be so fast, because if you analyze the turn on of this MOSFET, it will be just like I don't know. Yeah, it will be just 24 nanoseconds with a gate resistor, which is very fast. Now, which is very fast. Yeah, so that's basically it. For the gate charge instead, basically it is another similar circuit, but instead of using the pulse here, you just put a constant voltage. So instead of using a pulse generator, you use just a constant voltage, so that you can recharge with a linear way the gate capacitance. So now if you run the simulation, what you let's destroy this one because we don't need it. Again, this is a comparison between well, let's destroy this one. If you see the gate charge, you see that there is a big difference between MOSFET and silicon and APC converters. So I will show you the difference between two power MOSFET before, and so let's this has 17 coulomb as a charge, and let's put instead another with 40 nanocoulomb as gate charge. So let's see these two instead. So as you can see, let's run the simulation just for 100 microseconds because this is very fast. The gate charge characteristics is characterized by a constant is characterized by a behavior which is basically like this. You have seen maybe this QG, and this is the VG, and this is basically the threshold voltage, VTH, and this is the plateau voltage. Basically, when you reach this stage, you are seeing a capacitance which is basically infinite because there is the Miller theorem, and the capacitance between the gate and the source is amplified, and so it is normal enough to expect something like this. Now, if I'm zooming it right, so it is rising very fast towards the turn on of the transistor, and then you have the plateau voltage more or less 2-3 volts higher than the threshold voltage, or even higher. As you can see, this is a typical waveform of the gate charge. You can multiply the time times the current. For instance, IM1. You can do that with the ID M1 times ID M1. Why I'm doing this? Because if you multiply, because there is a reason of this, because if you multiply, so here you have the time, But if you multiply the time for the current, you're gonna have a charge. So, and now this graph will have a meaning, because this then will be the amount of charge to do something, to turn on the transistor, to arrive at a certain voltage. So now that what you're reading is the charge. So as you can see, in order to reach some voltage for the MOSFET, you have to provide 1421 nanocoulomb of charge. Yes, naturally this is the current of M1, which we can be... No, it should be the same. Should be the same. Yes, it is the same, so it doesn't make any difference. So that's how you simulate correctly and give meaning to the gate charge, because you have to multiply your time for the current, and then you will obtain the charge. Now, if you click Control, you will parametric blocks can be integrated. Ma non è un plot parametrico questo, cosa c'entra? Non è un plot, ma dov'è il parametro? Che cosa sto parametrizzando? Cos'è un plot parametrico? Dov'è il parametro? Ma tuo zio è un parametro. Cosa vuol dire? Ma dov'è il parametro? Io non sto parametrizzando nulla. Sto deficiente di Spice. Vabbè, va. Sorry, so parametric blocks can be integrated, I don't know why, but okay. So let's close the video for now. Thank you for your attention.